Yes. Yes. Oh, yes.
Yes.
Wow. Sure, maybe not.
But sure, maybe not.
Oh, okay.
Probably.
So as I know, currently we haven't found anything lah, but maybe there is, but we don't know. We just don't know. Okay. So basically, you can. So if currently we haven't found any life, can for example lah. So what
Yes.
is
Yes.
actually
Oh, yes.
astrobiologists
Yes.
do
Wow.
if we
Sure,
haven't
maybe
found
not. But
anything?
sure, maybe not.
Oh,
So what
okay.
are they
So
doing?
as I know,
So
currently
actually
we
they are doing,
haven't
they're
found
studying the
anything lah,
environment of
but
the other
maybe there
planet,
is, but we
for
don't know.
example,
We
something like
just
that.
don't
Like if
know.
there is any
Okay.
bacteria, any
So
life
basically,
on the other planet.
you can.
Previously, some maybe in Mars. Previously, there is
So
a
if
life, for
currently we haven't
example.
found any life, can for example lah.
So
So
yes.
what
You
is
can
actually
Google about the
astrobiologists
SETI
do
project.
if we
They are
haven't found
looking
anything?
for extraterrestrial
Oh,
life, and
okay.
currently
So
they
as I
spend like $1 billion kan, to look if there is any life out there lah. So I think in Malaysia we have one astrobiologist, which is I think maybe one, if I'm not mistaken lah, maybe more. So it is Dr. Kuhan from Institute of Climate Change UKM. He is I think he is the one astrobiologist that I know in Malaysia lah. Okay, so next is about heliophysics. Have you heard about heliophysics? So basically, yes, no, never heard about helio. Okay, it's okay. So basically, it's just a term. Actually, helio is about the sun, anything about the sun. So basically, we study the impact of the suns to the environment lah, to the Earth environment, to other environment in the solar system lah. So in Malaysia, I think this group is very active. There are many researchers doing this in Malaysia, including me. Okay, I'm also one of heliophysicists. Okay. So next is astroseismology, astrochemistry. I think from the names you should know lah what is it kan. And the last one here is astroarchaeology. Okay, astroarchaeology. This is the one that I think this is interesting. And this one is quite new to me lah. I heard this about. Hello. Anything? I heard about astroarchaeology several years ago lah. So basically, as it name, archaeology kan, archaeology. So because recently there is researcher from USM, if I'm not mistaken, from USM lah kan, from USM. They found that lembah Bujang in Kedah, that is one of astroarchaeological site in Malaysia. Meaning that that building or that site is related to astronomy. Like Stonehenge in UK kan. So I think that a place is we should keep lah that place kan. So I think it has a potential to become a tourism site in Kedah if they keep it lah. Otherwise, I think we'll lose everything in Lembah Bujang tu. So I think there are so many others lah. I think there are many more than 10 branch, I think. But I just list some of the topic lah. The important part here is astrophysics, meaning that astrophysics is a subtopic in astronomy. So basically, this is several subject listed here. Basically, if you are majoring in astronomy, for example, in the other university lah, they are major in astronomy, for example, they have to take several other subject lah. Like this one, they have several different subject for each topic, like stars from sun to black hole, solar system, and so on lah. They are separate subject, separate course for each topic. But here in UTM, we only have one subject, which is astrophysics. So basically, we need to combine all these astronomical, all the other other related topic into one lah. So because we need to know about the astronomical object event before we go into the astrophysics. So basically, I just put all this topic inside our course information, and I will we will see lah each of this topic. We will see the physical mechanism of each topic lah. We will see the astrophysics part of that for each topic.
So for example, from sun to black holes ni, basically in astrophysics we will study the evolution of the star lah, from nebula to black hole for example, maybe from nebula to a neutron star or whatsoever lah. There is a characteristic lah for a star to become, for example, black hole or neutron star ke, white dwarf ke, for example. So we will study that in this topic. Okay, it is astronomical topic, but we will look deep into that topic lah. This is the some of the example of that astronomy subject lah. So next, so here are the different lah, not different. Here yalah different lah kot. Different between astronomy and astrophysics. Okay, all about astro lah. So basically, in astronomy we study the universe beyond the Earth atmosphere. So we measure the positions, motions, brightness, cluster of galaxy, quasar, and etc. lah. Okay, so so basically we it's related to the measurement, the position and the distance, the position of that object lah. So the main branch are astrometry, celestial mechanics, and astrophysics. See, astrophysics is the subtopic in astronomy. So basically, astronomers use instruments to observe universe and to see what they are. Basically, astronomy is related to observation. So we just observe what the object outside there. We just do if you do the observation, then it's an astronomy lah. So in for astrophysics, which is a subtopic of astronomy kan. So this is the application of physical processes of small and medium sized structure in the universe. So why it's small and medium? So basically, if you study the universe as a whole, we study the universe as a whole, so meaning that that's cosmology, the other topic. Not astrophysics lah. So basically we astrophysics study each object separate lah. For example, one star to one star, one cluster to one cluster, one galaxy to one galaxy. So like cosmology, they will study, for example, the expansion of universe and whatsoever lah. So related to universe as a whole. That one is cosmology. Okay. So basically, astrophysics to understand and interpret them. Energy of stars, planet, black holes, etc., their formation, evolution, and their future. So basically, astrophysicists study how the universe work, okay, and what they are lah. So basically, for example, meaning that astrophysics is something like we use fundamental physics. Okay, we use fundamental physics to understand or to explain all the astronomical phenomena or properties lah. Okay. And also we understand their behavior, their motion and everything lah. For example, we have planets that orbiting around the sun kan. So for that, so in Newton mechanics, we believe that the motion is due to gravitational force. I think we will learn this. You will learn this in Newton mechanics subject kot, about the gravitational force. So basically it depends on the mass and distance between the two objects lah kan. And then after that we have also the other theory, which is a theory of general relativity. Basically it's explain what the gravity is kan. So basically the motion of the planet is due to curvature of space-time for the object with a mass lah. For example, is due to curvature of space-time lah. So and there are many others lah, many other event and properties that can be explained by astrophysicists lah. Okay. So next, I have time until sampai bila ni ya? Tiba-tiba masuk huruf astrologi. Until 3? Oh, lagi 10 minit je. So nak masuk astrologi ke nak masuk CI terus? Any suggestion? Can I skip this one or just go to CI? Anyone? We'll skip, Doctor. Okay, so we'll skip this part lah. Okay, so basically, we will see the content lah, the content from astrophysics course. This is the I take from course information of that subject lah. So basically, for chapter 1, it's about introduction of the subject lah. Basically, we will see the celestial sphere, which is the imaginary sphere lah. So, and we'll see the coordinate systems and the motion of the object in the sky. This one is in chapter 1. In chapter 2, it's about gravitation and celestial mechanics lah. So we start with the pre-discovery of astrophysics until Newton gravitation and Kepler's law. Basically, it's about the motion of the planet of the rocket, for example lah. And chapter 3 is about the EM radiation, electromagnetic radiation. Okay, so I think you have learned about this in optics ke, in you have EM subject kan? I think I'm sure that you know about this topic. So I just in fourth year we just go through this topic. Okay. So the fourth one is about the astronomical instrumentation lah. So basically it's about the properties of telescope and the observation at a certain wavelength, because normally we have a optical telescope that observe object at a visible light, and we also have the other type of telescope that we call infrared telescope, radio telescope. It's all depends on the wavelength and the purpose of that instrument lah. For example, if you have a infrared telescope, we want to see a very young star, for example. And chapter 5 is about stellar distances and brightness. Okay, basically we measure brightness of the star based on a color index. Okay, because we need this color index because basically our eyes is sensitive to a greenish, yellowish to greenish color. And from the photography, photograph plate is sensitive to blue color. If I'm not mistaken, blue color lah kot. So from both observation, actually we can get different brightness of the same object. From the eyes, maybe the object A looks brighter, object B looks fainter lah. So that's why we have this color index, so that we will get the true brightness of that object lah, which one is a really brighter object. Okay, so that's why the topic is about that one lah. Next is about the sun and solar system. So basically we study about the sun activity of the sun and the impact of the sun to the environment lah, to the sun's environment, to the earth, for example. And then it's about the planet beyond the solar system, we call exoplanet. So I think this topic is currently for researcher lah, for astronomy, it's growing very rapid, I think, because almost very frequent, we always heard that they found a new planet here, they found somewhere there, macam tu lah. So as I think we have better observation tools, they can get more information lah. It can detect a planet easier than before lah. Maybe that's why we heard about that. I don't know if you heard about a new planet has been found ke apa ke, but I always heard about that lah. So that's chapter 7, and chapter 8 it's about binary star. Okay, so binary star is which is two or more star that gravitationally bounded. Okay, basically the star is orbiting each other lah. So because in this universe, about 85% of the star are in a binary system. So what are the importance of this binary system? It is very important in astronomy because this is the only, I mean, not only, this is one of the accurate method to estimate a mass of the star. Does quantum physics related to astrophysics? If I will answer that after this lah. somehow it's related, but it's two different branch. Okay, there is a quantum in astrophysics, because if you go deep into the the particle inside the core of the star, then I think we will somehow go into quantum physics. It's about the particle. Okay. Sampai mana tadi? Salah structure. So, berapa ketiga dah? Belum. Okay, so and then chapter 8 it was about binary star. Chapter 9, stellar classification. Basically based on what parameter lah, we classify the star based on temperature ke, based on the size ke, mass ke, the macam-macam lah. Then next is chapter 10 is stellar structure. Chapter 11 is stellar formation and evolution. Basically, we will see how the star, evolution of the star from dust into the graveyard lah in chapter 12. The fate of the star lah. Whether it will become a white dwarf ke, neutron star ke, pulsar ke, black hole. All of this is depends on the mass of the star. If very massive object will become a black hole, so less massive maybe will become a white dwarf or a brown dwarf, something like that lah. And for chapter 13 and chapter 12 about universe and galaxies, normally I will not go further into this topic lah, but we just see a very surface part lah of these two topic lah. Okay. So that's all about astrophysics punya topic in fourth year. So next is this one is about the software that we normally use in the class, but I will suggest you to install this two software juga kot, because it's very useful. This software normally the first one is Stellarium. This one is you can download it in your PC, but currently I think they have apps in Android code, but you can try lah if there is Stellarium. And the second one is Skyview. This one is apps, phone apps. So you can download it, but I think it quite makan space juga lah kot. So normally if you see the sky or see the night sky, sometimes you see some object like the stars or whatsoever. And if you see there are two bright object, maybe it's a Venus kan, but sometimes you are not sure what object is that. So normally we will just open the sky view. You just open the sky view in your phone and point it at the sky. So it will show what are the possible object behind your phone. So maybe it's quite handy lah. So you can know what are the object that you see at that night from this sky view apps. So it's very useful. So you don't need to guess lah what is that. We just use this kind of apps. So lagi sikit 1 minit. Oh, so this one is before we end, I would like to share lah some great news. These are some great news from astronomical community. So first of all, have you heard about this one, James Webb Space Telescope? Anyone heard about this? Because I found this in bulletin utama pun ada dekat, I think dekat bulletin utama ada itu. So no one heard about James Webb? Never heard about it? No. Oh, most of you not heard about it. So it's okay, don't worry. So currently this is have you heard about Hubble Space Telescope? Hubble Space Telescope, have you heard about that? Yes. Okay, this one is a successor to Hubble. Basically Hubble with a 3 meter diameter, but this one, James Webb is with a 6.5 meter in diameter. Basically Hubble is the size of a bus, and James Webb is a size of a tennis court. Basically telescope, we need a bigger telescope because we want to collect more light. We want to have more light get into the telescope. That's why we need, for the telescope, the most important part is the size. Okay. So that's why currently they just launched this telescope on 25th December 2021. Recently, last 2 week apa during Christmas kan. So it will currently it is on its way to L2 point, which is Lagrange point. I think we will see. We will learn about that lah later. So if you are interested about this, you can follow their updates. Currently they are still in a deployment punya stage. They currently are opening this part and opening that part. Still on the way to the apa L2 point too. So I believe after this we will receive much more beautiful picture from our universe. Before this, we always we will see a beautiful picture from Hubble Space Telescope kan. So after this, we will see. I think it's expected that it can give result in 6 months after this. Maybe next year, this year, in middle of this year, we will see a better picture of a galaxy, better picture of a nebula, for example. So I am very excited about that. So tu je lah kot. But we have another good news. But I still have time ke? So should I end here?
Okay, thank you, Dr. Soila, for the fruitful sharing session. Okay,
Okay.
Dr. Soila, we do receive lots of communication. If you're looking into currently live more than 50 participants from WebEx. So I just reflect to the question from WebEx from Adriana Sofia. Assalamualaikum, Doctor. If I interested to be an astrophysicist, so what should I do after my degree?
I don't consider myself as astrophysicist lah, but we have a lot of astrophysicists in Malaysia. We have the first astrophysicist is Dr. Mazlan, if you know. And then we have a very famous one is Dr. Adlika. I think he is the first Malaysian who found a black hole. I think first of all, what I can see is maybe you need to further your study to master or PhD lah kot. In this area lah, in the astrophysics. But there is also position in Malaysian Space Agency (MISA), such as research officer. But I think if you want to go further deep into this area, you need to do master and PhD lah kot.
Okay. Okay, thank you, Dr. Sala. There's another from Azraf. So what kind of this topic student really difficult to score?
Most of the topic sama je kot. The difficult one is for me, the difficult one is celestial mechanics for me. I don't know about the students. And the other one is stellar structure. That one is difficult for me. I'm not sure. I think sometimes I don't put that in the question in the test or final exam. That's why I don't know about the score of the students about these two topics.
All right. Okay, thank you so much, Dr. Sala, for the great sharing session and good sharing experience with us just now. Okay, now I would like to welcome our second speaker, Dr. Yap Yunzen. He was honored as a Doctor PhD in Science from Osaka University, Japan. He also visited the Research Center for Quantum Technologies, National University of Singapore, and visiting academic staff in Graduate School of Engineering Science, Osaka University. So how are you, Doctor? Dr. Yap, how are you? Okay, I cannot hear you. Okay. No, Doctor.
Dr. Yap, it looks like you are still muted. Mute.
Okay.
Okay, Doctor. Sorry, Doctor, I can hear you. Cannot.
Testing. Boleh dengar? Can you hear me?
Okay,
Hi.
boleh.
Yes, yes.
Oh,
Yeah.
Okay, I can hear you. Okay.
sorry.
Okay, Doctor Yap, how are you?
I'm good. I'm good.
Okay. Okay, that's good. So, Doctor Yap, Chinese New Year is just around the corner. So, what is your preparation? Are you excited?
Um, no preparation yet at the
No.
moment. Still very busy with the other stuff.
So, I hope, okay, may this Chinese New Year will bring you a good health, prosperity, and happiness for you and your family.
Thank you.
Okay.
Thank you.
So, okay. So, without further ado, I will pass our sharing session to Dr. Yap. To Dr. Yap to share his experience in astrophysics and quantum. Okay, Dr. Yap, the floor is yours.
Okay. Thank you very much. Let me share my screen first. Hold on. Sharing the wrong screen. Okay. You can see my screen. My desktop.
So far, I can see.
Okay. Okay.
Okay.
Okay. Very good afternoon. So my name is Yap Yung Sing. I'm a lecturer in the Department of Physics. So I'm mostly teaching for now fourth year courses. And today I'm going to talk about a little bit about quantum computers, more specifically on what is a quantum computer, what are the progress, and what are the opportunities. So these are work done by a few groups in Singapore and also in Japan. And basically, if you have heard of quantum computers, what they are used for, or maybe as a physics student, because you'll be learning about quantum mechanics, you might be interested to know a little bit about this. So before we go into quantum computer first, let's just review back what we know about classical computers. So a classical computer is the laptop that you're using right now, or even supercomputers that are like in Japan or in US, those very big computers that they fill up the whole ground floor or something like that. Those are supercomputers, but they are still classical computers. And the reason being that they actually use, for example, voltage levels. Okay, or if you are using hard disk, your hard disk is actually storing information in magnetic orientation. So they could be representing 0 and 1. So here the diagram here is actually the voltage level. So you have I can't seem to. Okay. Can you see my mouse? I hope you can.
Yes, yes.
Okay. So for the normal voltage level, you have, for example, low here, 0 volts, and then it represents the logic 0. 1 represents the logic 1. And if you have 1 bit, then you typically store one information. So like 0 or 1, that's the normal idea. And if you have 2 bits, you can store any combination of these 00, 01, 10, 11. So if you have read about quantum computers, then you know what I'm going to talk about next. But before we go next into quantum computers, just classically, if we want to edit this information, typically we use transistors or some combination of diodes, actually more towards transistors now. So you have, for example, the 0 going inside here through the NOT gate, and then it comes out as 1 because this NOT gate changes from 0 to 1. If you put in 1, then it changes to 0. That's the basic idea of classical computers. Now for a quantum computer, and my slide is not moving. Not so sure why. Sorry, let me stop sharing for a little while. Sorry, technical problem.
Okay.
Okay, I think my PowerPoint crashed. So sorry. Definitely crash. I can't control my PowerPoint. Sorry about that. I need to terminate first. Do you still see my screen?
No, Doctor.
Oh, okay. Just a second. I need to terminate PowerPoint. PowerPoint. Yeah. So normally we have this kind of joke. We need a quantum computer, then only we can, present properly. Yeah, that is one of the normal jokes that we encounter in our quantum computing group. We need a quantum computer now. Okay, let me restart back PowerPoint. So sorry. Okay.
Okay, now I can see your screen.
Okay, good. Okay, now it's moving again. So for a quantum computer, we don't actually use voltages or magnetic storage like your hard disk, but we actually use energy levels. So energy levels are quantum in nature. So they exist. I mean, they exist in, for example, everywhere. Like when you're talking about electron spin states or energy levels of the electrons. So you have the ground state, the first excited state, the second excited state, and so on and so forth. And by using those energy levels, you can actually store information similar to your classical, like 0 and 1, but you can also store for both at the same time, meaning that uh, um, if you have two energy levels like your ground here and then your excited state here. So normally we can actually keep information in either the ground state or the excited state, and we can actually put them in between of these two, not in between here, not in between this particular space, but more of a superposition of both, something like this. Okay, which actually tells the probability of you getting one state and the probability of you getting the 0 state. So that is what we can do with energy levels. You can't do this with voltages. So it's not the same like you're saying you have 0 volts and 5 volts, and then if you have 2.5, that is like a superposition of both. No. If you realize on the top left here, where I have this small circle, this is what we call a block sphere. Okay, so this block sphere is how we show or how we store information on a quantum qubit. So we call it qubit as in quantum bit. Okay, So the 0 cat is at the top and the 1 cat is at the bottom, and the red dot there is your quantum state. So it can be anywhere on this 3D. So if you imagine the Earth, the globe, then the information is on the surface of the globe. No? Okay, so now the exciting part is that when you have 1 qubit, you can store information on both energy levels. But when you have 2 qubits, you have a different set of energy levels, 0, 0, 0, 1, 1, 0, and 1, 1. So the interesting part about that is that then you can superposition all of those. You can actually have probabilities between the first, second, third, and fourth. So 0, 0, 0, 1, 1, 0, and 1, 1. And they can store all of this together at the same time. The more number of qubits you have, for example, 3 qubits, then you have 3 to the power of 2 to the power of 3. And that's a lot. And if you have 32 qubits, that's approximately 10 to the power of 9. And you have 64 qubits, that's 10 to the power of 19. So our computer, classical computer, it's typically 64-bit, right? But when it's 64-bit, when it processes information, the classical computer, it only processes one state at a time. So 0, 0, 0, 1, 0. That's all. You want to process the next information, reset everything, and send the next bit inside. But for quantum computer, you don't need to do that. The information is stored for all states at the same time. So you can process all of them at the same time as well. And how do they actually look like? So I believe some of you might have seen this. The middle one here is IBM quantum computer, and the one on the right here is Google quantum computer. So this was previously the leading scientist with the group, John Martinez, Professor John Martinez. D-Wave is another. This is the quantum computer in my group in Singapore in CQT, and in Japan. You can't see my face, but yeah, that long hair guy with that sort of like a vest, that's me. That is a smaller version of that. And if you open all of these are called dilution refrigerators. If you open all of that, you will see all of these layers here, multiple layers, as you can see here. This is what you normally don't see on the internet. Is all these layers. You normally see either it's closed or it's fully open. So in between 3 to 4 layers of protection. The first is the outer vacuum protection. Then you have this silver that looks like aluminum foil, but trust me, it's not. It's the same material that they use for satellites. And then you have high purity copper, high purity oxygen-free copper. That means there's actually very low oxygen impurity inside, and there are actually a few more inside there. So this dilution refrigerator cools down the sample by stages. So from the top here, this is at room temperature. So this is connected at the way at the top. Then the second stage here is about 50 Kelvin. The third stage here is about 3 Kelvin, and you go down all the way to 10 millikelvin. So 10 millikelvin is near the absolute temperature, which is, 0.01 Kelvin. It's actually colder than outer space. So outer space is about 2 point something Kelvin. So this is actually colder than that. And in this 10 millikelvin stage, right at the bottom here, that is where we will put our equivalent of our CPU, but we don't call it CPU, we call it QPU, quantum processor. And we put down there to actually perform our experiments. But again, that depends on what system that you are using. The system, there's a few systems. People are still, working on this. The quantum computer right now is similar to computers those days when people were first building computers. So they were thinking, oh, what is a transistor? How do you use transistor to create a computers and whatnot? So some of the systems that are being investigated is the superconducting qubit. So it looks something like this. And this is the 10 qubit. So this is a single qubit over here. And over here we have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These 10 small dots here. Some people use photonic. This is by the China group. And this is Honeywell system. These are trapped ions. You can actually see ions here, and you can actually capture images of them. There are also many other systems like semiconductors, defect points, NMR, ESR, and etc. this BEC is Bose-Einstein condensate. You actually cool bosons until they actually reach the ground state and they form BEC. So all of them will actually clump together. Yeah, and there's a question there. I'll answer that a little bit later. Quantum computers, there's actually quite a few things that people are doing. So this was like what I showed you. These are one quantum computer. You can have another quantum computer, and you can actually, people are trying to connect quantum computers together. So you can actually try to connect it from cloud to cloud. Some people are trying to do that. Some people are trying to connect from the quantum processor to another quantum processor. Okay, so when they do that, they some of them actually just use one dilution refrigerator, but they put two QPUs inside, two quantum processors inside. So imagine like your computer, you have two CPUs. So one dilution refrigerator with two quantum processors, and you try to carry out operations like that. So the ones that between two dilution refrigerators looks something like this. So if you can see here, this white jar here on the left, on the right are two different systems, and they try to just join them up. So people are doing many things, are trying to investigate many different stuff, and people are also trying to use quantum telecommunication to build the quantum internet, for example. So they can either send signals from this level. So this is at room temperature to room temperature, and you can actually use photonic systems to do that. Some people are trying to do with satellites between cities. Okay, so these are all published work. That means there are people actually working in this, and there's actually a lot of applications for this. So people are trying to use quantum computers to simulate quantum systems, chemistries. You simply can't understand some things because the original process is quantum in nature. So like chemistry, actually, when you are mixing two chemicals and whatnot, those are actually all quantum in nature. And to actually understand them, what's going on, you can use a supercomputer, a classical system, but first, it will never reach a certain level of accuracy. And second, even if it does, you will need a very, very long time. Unlike when you're using a quantum computer, you'll be able to simulate more accurately or at a much more shorter time. So one would be on an exponential time scale, one would be on a polynomial time scale. So the quantum computer is on a polynomial, and the classical computer is on exponential time scale. So these are just like some of the applications available. I'm just not going to go through that, but even classical, we already have people doing like AI and whatnot, right? So imagine if you can do this much faster using a quantum computer. So that's why people are now, there's a hype of scientists around the world, physicists, not only physicists, but people of different fields trying to go into quantum computers now. So this is from Volkswagen and Lisbon, Portugal. They are trying to use a D-Wave quantum processor to find the bus route in real time. So it's like your Google map or something, but this, they are trying to use a quantum processor to do that. So you can use it for logistics, you can use it for floor designs in factories, for navigation and whatnot. No? So there are actually a lot of applications. It's been around for a long time. People are, it's getting more popular. It's been around since 1996 and even before. Okay, so recently in 2019, there was this 53 qubit quantum supremacy demonstration and whatnot. No? And because there's so many applications, promising applications, a lot of countries are actually investing in quantum computers. So you have UK, Canada, Japan, Singapore itself, like CQT, they have been investing up to 80 million. US, they have a national initiative for that. Okay, and then what I would like to point out is like the US, the Department of Energy. You might be wondering, why is the Department of Energy interested in this? But if you think about it, if you use a quantum computer and you use a classical computer, And like I mentioned just now, you use a classical computer, you need to process it for a very long time. So if you use a quantum computer, it might finish much more shorter. So the example here is like 200 seconds versus 10,000 years. So in 200 seconds, you only use 1 kilowatt compared to um, um, a classical system, which you use like 1,000 megawatt hour. So this is in log scale. This is not in linear scale. This is actually in log scale. Yeah, and there's a lot of people investing in this and whatnot. So I think this is sort of like um, some people will actually call this the bubble. If you heard of the term bubble, like it's like people are investing a lot, and then it's about to burst. Burst meaning that the economy, I mean, that particular economy might fall. So normally people refer this to housing. So when you buy a house, the house prices are increasing, so that they are saying there's a bubble for that. And when it bursts, suddenly the house prices will be very cheap because there's too much houses and nobody wants to buy. So there are questions whether is the quantum technology a bubble and is it about to burst? So as you can see, this is still quite recent, 2020. Now it's 2022, just a few days. And then you have in nature, they call it the gold rush, the quantum gold rush. So my take on this is that there are a lot of people working on this, and currently there are jobs for this. So you can actually work at, for example, IBM, they call this uh, research quantum experimentalist. You have quantum hardware lead, quantum engineer. So quantum engineering is now real. It's not something that, oh, this is made up of there's nothing. So these are companies offering positions, quantum engineer and whatnot. And in Google, there are actually academic programs for that, and some universities are starting to offer quantum engineering courses, programs, as well as lecturers or professors in that. So yeah, that's the interesting part about quantum computing or quantum information processing in general. So if you are doing postdoc, if you're going to study your postgraduates, then even publications have also increased. So for specifically for quantum science and technology. So this is a new system. And if you're interested, you can actually try to use quantum computers. They are available online by IBM. So this, you have to register, you have to learn how to use it, and these are some of those systems linked to a real quantum computer. So you can actually simulate it first, then you can queue it up, and then when your time comes, it will process it in the quantum computer and send you back the result. So it's actually possible to do that. So here are some examples, screenshots that I took. So there's IBM Q Jakarta, IBM Q Santiago, but this is actually not in Jakarta. Hopefully, one next time there will be one IBM Q Kuala Lumpur or Johor or something. And yeah, I think these are just small fraction of companies which are investing into quantum computers. So if you just Google online, there's actually a big group of companies, scientists, fans, because like I saying, people who are trying to move from another field, like just now where I was saying Volkswagen and whatnot. So all of those different companies are now trying, different applications are now trying to go into quantum computing. So they are trying to learn how to use quantum computers. So I think that's all as an introduction from me. Yeah, thank you very much for listening. And if there's any questions, I'd be more than willing to answer them.
Okay. Thank you, Dr. Yap. That was a presentation. I truly inspired with your amazing knowledge and sharing session just now. So that's a question from Aina Amira. Doctor, do we need to be good in chemistry in order to score this subject?
So it depends on what you are doing actually. So there are some people who are actually trying to find new materials to build a quantum computer. For chemistry, Initially, last time, yes, because people were using NMR and ESR, so you need new systems, new materials for that. But now, not so, because people stop using NMR and ESR and have moved on to trap ions and superconducting qubits. Chemistry, not so much now, more to microfabrication. Um, yeah, so that's the answer to that question. And there's
Okay.
no test here.
Okay. Okay, thank you, Dr. Yap. Okay,
Okay.
there's another question from Fariza Hanim. Okay, hi doctor, do we have quantum computer operating at room temperature?
Yes, so to speak, but not really for many number of qubits. It's possible to use what we call, for example, nitrogen vacancy. So NV for short. NV centers are actually inside diamonds. So girls like diamonds, right? So it's the same diamond that you go and buy for your rings or your earrings. But if you buy diamonds, normally you want to choose those which are very um, clear. They have little impurities. They are not yellow. They are very white. But here's the thing: when they are yellow, they actually have nitrogen impurities, and those nitrogen impurities create defects in those carbon lattices to form NV centers. And the NV centers are the one that are used for quantum computer. So those can work at room temperature, but it's not easy to create that because diamonds are um, very tough. Okay, you want to arrange those NV centers is actually very difficult. So people are trying to do that with artificial synthetic diamonds and to actually put the nitrogen vacancies at certain locations. So at the moment, we don't have a quantum computer operating at room temperature. Most of it that we are trying to build are still at millikelvin. But yeah, maybe, who knows, if somebody make a breakthrough in some other technology, then possible.
Okay. Thank you, Dr. Yap and Dr. Soila, for the response and answering the question, a lots of questions, and for the great sharing session just now. So I hope this sharing session could help us inspire more, and it was a pleasure to have Dr. Yap and Dr. Soila with us. So now I would like to welcome Dr. Noain Hussein to conclude the day.
Hi, thank you, moderator Aina Traf. Thank you very much to our speakers, our friends from Department of Physics, Dr. Yap and Dr. Suhaila. Thank you for your willingness to spend your afternoon. So thank you very much, and congratulations to everybody for the success of our series. Okay, tepuk tangan sendiri dulu, sendiri je dengar, saya tepuk. Okay, thank you very much, especially to Dr. Salwa for arranging this session. And yeah, because if I can share a little bit in my section at least, and I believe I also discuss with discuss with Dr. Salwa that in Introduction to Physics class, usually when we talk about, I tanyalah mekanik, optics, nanti balik-balik mereka akan tanya juga, kalau kuantum macam mana doktor? Astrophysics macam mana doktor? I rasa sebut lah dengan Dr. Yap, Dr. Suhaila. So terus bawa, and then we have this session. So I hope all students already know, dengar Dr. Suhaila macam mana, kenal Dr. Yap. So after this, bolehlah cari sendiri, reach Dr. Yap dan Dr. Suhaila sendiri kan. Dr. Yap dengan Dr. Suhaila tak lari kan, if the students would like to have further discussion. And yeah, so it's just for start, and I believe that boleh banyak-banyak lagi lah sembang in future. So you want to plan your project, final year project, or future career ke, ataupun nak sambung study, semua tu kita ambil tahu banyak lagi lah. We try to understand more field, more bidang, and then all the best when there is time for you to make decision which field that you want to explore more. For now, first year, nama pun Introduction to Physics, right? So for now, first year, explore semua. Betul kan? Aina Traf pun explore personality dia sebagai moderator. So macam-macam lah yang kita boleh explore in this journey Introduction to Physics. So that's all for me for today.
Back to our moderator.
Okay, terima kasih Dr. Noain atas ucapan itu tadi. Saya juga ingin mengucapkan terima kasih kepada para penganjur yang telah berusaha untuk memastikan sesi ini berlangsung. Okay, so before we end the session, we would like to invite the Honorable Speaker Dr. Yap and Dr. Sohaila to receive our appreciation certificate. Okay.
Tepuk tangan. Oh, boleh tepuk tangan virtual Dr. Salwa baru saya teringat.
Okay. Okay, thank you. Okay, so we have come to the end of the session. Thank you for all who attending today. I hope you guys enjoy as well as gain some benefit and knowledge along the way. So, okay, everyone, please turn on your camera. Have a quick photo session.
Okay, Hazim boleh ni dulu. Hazim tolong turunkan ni. I nak ambil gambar yang semua ni. Okay, I hope the students still not tak tinggalkan dulu ni. Tak left lagi. Sekejap I nak ambil gambar.
Please stay seated.
So, tolong Hazim tolong remove Ainatra also from the stage. Okay.
Ada Puan Masliati, Dr. Razif, ada Dr. Fariza. Ain sebut Fariza je, ada Dr. Fariza tu. Hebat orang datang ni tengok Ain.
Okay, Hazim removekan juga Dr. Ain. Sekejap nak ambil gambar. Okay. Sekejap Okay. 1, 2, smile. Okay, sekejap saya paste dulu. Sekejap ya. Okay, one more time. Okay. 1, 2. Alright. Okay, thank you everyone.
Thank you, congratulations.
Okay, thank you Dr. Shaila, Dr. Yap and all the lecturers and also the students. Terima kasih semua.